The title of the talk I will give is A Lower Bound on the Number of Colors Needed to Nicely Color a Sphere. I start with the motivation of the problem I worked on. The Hadwiger-Nelson problem is a well-known problem in combinatorial geometry. It asks for the chromatic number of the graph of unit distances on the plane, or simply the chromatic number of the plane. This means that we are looking for the minimum number of colors needed to color the points of the Euclidean plane, so that no two having a distance of 1 have the same color. Until recently, the best known lower bound was 4, while the best known upper bound was 7. The lower bound was first obtained by Nelson, who first formulated the problem, but probably the most simple way to prove it is via the so-called Moser spindle, a graph discovered by the Moser brothers shown in the image on the left, which can be embedded into the plane with all of its neighboring pairs of vertices having distance 1 and has a chromatic number of 4. On the right, we can see a 7 coloring constructed by Isbell, which proves that the chromatic number of the plane is at most 7. A little bit surprisingly, the above-mentioned upper bound is still the best we know, and up until 2018, the lower bound was also the best. But then, de Grey proved that in fact at least 5 colors are needed by showing a unit distance graph that cannot be 4-colored. His proof used computer resistance because the graph he examined was too large for the result being humanly verifiable. Thus, it was a natural goal to find a simpler proof. The Polymath 16 project was launched with this purpose, but it also tried to obtain new results related to the Hadwiger-Nelson problem. As a participant of the Polymath project, this is the reason why I started to work on this problem. Now I will talk about some variants of the Hadwiger-Nelson problem. Many variants exist, some of them impose extra restrictions on the colorings of the plane. For example, it is known from Falconer since 1981 that if the color classes have to be measurable sets, then at least 5 colors are needed, which is now also known for all colorings. Now call a region in the plane bounded by a Jordan curve a tile. Also, call a coloring of the plane where the color classes are disjoint unions of tiles a tiling. Townsend proved that all tilings of the plane need to use at least 6 colors. It is natural to ask about the colors of the borders in a tiling, but as a consequence of the De Bruyn-Erdős theorem, they don't affect the minimum number of colors needed. Thomasson also considered some extra conditions, calling tilings satisfying these nice. Specifically, he imposed that the tiles have a diameter strictly smaller than 1, and the distances between different tiles of the same color be strictly larger than 1. This is a stronger definition than the original in 2 ways. Firstly, when talking about tilings, we allow tiles to have a diameter 1 if the borders are colored appropriately. Secondly, in a general tiling, it would be possible to have very small tiles very close to each other. The only restriction being that no 2 points of 2 tiles of the same color have distance 1. Thomasson also required the tiles to be simply connected, though I do not. Indeed, some tilings I define violate this condition. Also, he actually proved the statement for a wider family of surfaces instead of only planes. These include large enough spheres among others. As implied above, another variant is to ask the question for spheres or other surfaces instead of planes. The definition goes the same way. Now we have to color the points of a sphere with no 2 points of distance 1 having the same color. Here, we in fact get multitudes of problems as this number might depend on the radius of the sphere. We might also wonder whether we should use Euclidean distance in the space or spherical distance, but normally we only have to make a conversion in the radius of the sphere to use one definition instead of the other one. The best known lower bound for the chromatic number of spheres with a large enough radius is 4. As for the upper bound, until recently the best known bound was 15, which comes from a construction by Radojcic and Toth coloring the 3-dimensional space with 15 colors. After submitting my paper, an upper bound of 7 for large enough spheres was obtained. We can also combine the 2 variants by asking how many colors are needed for a nice tiling of a sphere. I found that if a sphere has a radius of at least 18, then at least 8 colors are needed. Now I will present a sketch of the proof. I will use spherical distances, and thus I only suppose from the sphere to have a radius of 17.9, and later I can convert it to the version with Euclidean distance. Let's start with some preliminary statements. denote the adjacency graph of the tiles on S by G. If there is any point where more than 3 tiles meet, a multiple edge, or a cut vertex, then we can eliminate them relatively easily and end up with a graph G', which is a fully triangulated planar graph. Let's also draw G' on S by placing all vertices somewhere into their respective tiles and draw the edges so that they do not intersect. I will also require all points on the edges have distance less than 2 from both of the respective endpoints. Typically, all these conditions can be satisfied if the edges go through only the 2 tiles represented by the endpoints. In case the 2 tiles only meet in one point, but their corresponding vertices are still connected with an edge in G', then we still can draw the edges if we are careful enough. Now we color the vertices of G', and from now on we will only care about G'. It is enough to know that no 2 vertices with graph distance at most 2 have the same color, since if 2 neighboring vertices had the same color, they would correspond to tiles that have distance 0, which is a contradiction, while if they had graph distance 2, then their distance would still be less than 1, as their common neighbor would have diameter less than 1. Also, this means that all vertices of G' have degree at most 6, as any vertex with degree more than 6 would have a neighbor of the same color as itself or 2 neighbors of the same color. And from here, since G' is a fully triangulated planar graph, there must be at most 12 vertices that have degree less than 6. I will refer to these vertices as irregular vertices. Also, for any irregular vertex, let its multiplicity be the difference of 6 and its degree. The total number of irregular vertices counted with multiplicity is exactly 12. Now we continue with some other important lemmas. Since all neighboring vertices of G' have distance less than 2, the total length of the spherical segments connecting the neighboring vertices in a path P is less than double of the graph length of P. Note that this total length is not necessarily the same as the total length of the edges. Another lemma that will be used throughout the proof is that upon taking a simply connected subset of S and the subgraph of G' formed by the vertices and edges fully inside that, we can define a function phi that takes the subgraph to a subgraph of an infinite triangular grid. Also, we define it in a way that it will be a local isomorphy in some sense. 1. It preserves vertex edge incidence, and 2. For any vertex and any 2 edges ending in it, the number of edges between them, counting in the positive direction, remains the same. A similar lemma can be proved if the subset is homomorphic to S1 times the closed unit interval, but then all vertices and edges will go into possibly infinite sets of vertices and edges respectively. Now I define the curvature of a cycle. We take an arbitrary cycle C in G' and call one of its sides as inside. Then for all vertices V of C, we count the vertices of G' in the inside of C neighboring this particular vertex and subtract this number from 2. By summing up this number over all vertices V, we get the curvature of a cycle. Now comes another useful lemma. For any cycle C, its curvature is exactly 6 minus the number of irregular vertices inside C, counted with multiplicity. We can prove that by contracting C into a triangle. We use 2 kinds of steps. One kind is when we take an empty 3 cycle, or as I call it, a triangle inside C that has 2 sides lying on C, delete these 2 sides from C and replace them with the third side of the triangle. In such a step, the summand belonging to the vertex deleted from C is deleted from the sum, and this reduces C by 2, but the summands belonging to the other 2 vertices of the triangle increase by 1 each, so the curvature does not change. The other kind of step is when we take a triangle inside C that has 1 side lying on C, then we delete this side from C and replace it with the other 2 sides. This way, if the new vertex is an irregular vertex, then it increases the sum by its multiplicity minus 2, while the other 2 vertices of the triangle decrease the sum by 1 each. So in total, the curvature has been increased by the multiplicity of the newly added vertex. If the newly added vertex is not an irregular vertex, then the curvature was increased by 1 each because of the other 2 vertices of the triangle, but this vertex decreased by 2, so the curvature did not change. It is easy to see that such a step can always be performed if C is not a triangle and that the procedure always ends in finitely many steps. In the end, we get a triangle which has a curvature of 6. And since the curvature was increased by the sum of the multiplicities of the irregular vertices originally inside C, we have proved the statement. Now I define a kind of 7 coloring of the infinite triangular grid. It is not hard to prove that this is the only way to do so. Since it is constructed the same way as the pictured 7 coloring of the plane already shown in the introduction, I call these colorings Isbell colorings. First, color one of the vertices with color 1. Then color all of its neighbors with the other colors. Now tile the plane with the copies of this hexagon. It is important to know that the hexagonal part of the grid at the bottom left can only be colored with 7 colors with a part of an Isbell coloring. Also, if we color a triangular grid with an Isbell coloring, the graph in the bottom right determines by itself which coloring we have used. Now we can continue with the proof. Take a graph H on the irregular vertices, drawing an edge between those having a distance of at most 3 in G'. Now I will define 3 cases. Case 1, when H is connected, so essentially the irregular vertices are all close to each other. Case 2, when H has exactly 2 components, both consisting of 6 irregular vertices counted with multiplicity. Case 3, when none of the previous 2 cases hold. First, take a look at case 1. From H being connected, we can find a tree in G' on at most 34 vertices that contains all the irregular vertices. By using this, we can find a cycle C1 on at most 60 vertices that fits into a small disk and separates the irregular vertices from those outside the disk. So those vertices on the other side of C1 can be projected into the triangular grid. From this, we can see that all vertices of this side of C1 have graph distance of at most 10 from C1, as all vertices of this side of C1 are projected into the hexagon of smaller perimeter than C1, and the local isomorphism to the triangular grid guarantees that if from the image of some vertex we start going on a path to this hexagon, we always can do it in G' until we bump into C1. On the other hand, there exist vertices in this side that are very far away from C1, as C1 is inside a small disk. And by using the lemma about the graph length and the geometric length of a path, we get a contradiction. Now take a look at the second case, when H has 2 components, both with cardinality 6, counted with multiplicity. Now again, we can take the 2 cycles in 2 small disks, such that both have 6 vertices on both of their sides, and the most of S is between them. Now project this part into the triangular grid. Now all vertices and edges are projected into a set of vertices and edges respectively. From the lemma about the curvature of cycles, it can be shown that the curvature of both C2 and C3 is 0, thus the result of phi looks like something in the drawing. Now we can bring C2 closer to C3 with small steps shown in the figure. One possible step is that we choose a vertex in which C2 takes a sharp turn, and delete it and replace the 2 edges by the third edge of the corresponding triangle. Another possible step is that we choose a vertex in which C2 takes a mild turn and change C2 as it is shown. These steps do not increase the graph length of C2, and all of the edges of all of the cycles in the procedure have 2 endpoints both neighboring the same vertex in the previous cycle and both neighboring the same vertex in the next cycle. We even can make other kind of steps fulfilling these properties, like shifting C2 one step in a downwards direction if possible, or taking more than one step at the same time. If we are stuck with C2, we can move C3 in the direction of C2. In the end, they will coincide. With the above procedure, we defined a series of broken lines on S where the neighboring ones run close to each other. Also, all of them have graph length at most 24. But from a continuity argument, we can find one of them that includes 2 nearly antipodal points, which contradicts the lemma about the graph length and the geometric length of a path. Now take a look at the third case. In this case, we can find a cycle C4 not containing or neighboring any irregular points, separating them into 2 groups so that none of the groups have a cardinality divisible by 6. By examining the neighborhoods of the vertices of C4, we get that they are colored with Isbell colorings, and they are actually the same Isbell coloring. Also, every turn of C4 rotates the coloring accordingly, so C4 must have a curvature divisible by 6, otherwise we get a contradiction. But this way we also get a contradiction, as from the curvature lemma, C4 does not have a curvature divisible by 6. This finishes the proof of all three cases. Thank you for your attention.